All right, so today's topic is going to be cloud native build packs. I'll share my screen. Okay, and more specifically, it's continuously patched container images with a set of technologies that is based on cloud native build packs, including kpack and Paketo, and other additional tools we'll see along the way. So if you don't know me, my name is Oded. I work as a solution engineer at VMware Tanzu, based off of Israel, working with the broader Central EMEA region. This is my Twitter handle. This is my blog, odedia.org. You're welcome to head over there at the end of the session. And I'm generally working with our customers on everything related to, just getting a better understanding of how to do cloud native workloads, how to containerize their application, how to modernize to Kubernetes, to platforms and that are more developer-centric, things like that. So the agenda for today is going to be, again, just a quick brief of what exactly are Dockerfiles and how do they really help us get into containerized images very quickly, some of their pros and cons, and then we'll go over and discuss cloud native build packs, which is the topic of the day. And we'll also mention one open source implementation of this specification called Paketo. And we'll close talking about kpack, which is a Kubernetes-based solution for this project. Okay, so let's get started. So I'm sure most of you on the call are aware of Docker images, which, when you think about it, the way we should really start to call them is what we call OCI images, the Open Container Initiative images. They are the standard for everything related to platform portability. Okay, everything related to the ability to take an image, run it, be it locally, be it in a remote environment, be it on Kubernetes, in the public cloud, on-prem, wherever you want to run it. You basically can do it very, very easily because it contains everything you need in order to get an application up and running. It comes with an operating system. It contains all of the application source code and required dependencies. And it also contains the command or the entry point to start your application. So it's basically a self-contained environment that can run anywhere. It's pretty much the de facto standard today. Now, in order to create Docker images, there are multiple ways. There is actually more than one, but probably by far the most popular one is what we call the Dockerfiles. A Dockerfile is pretty much a script that defines exactly how you want the final image to look. So you have an example here on the right. You basically have a list of commands. You start from an existing image. In here, we use Ubuntu Bionic. You run multiple commands. You add arguments. You define environment variables. You copy files between your local machine to the target image, and then you define either commands or run commands or entry points to bootstrap the application itself. Okay, here on the right, actually, this is the Dockerfile to create the OpenJDK base image. So you can see how that looks like with the checksum and everything that you need to do it. So Dockerfiles are quite powerful. Because they're endlessly flexible, right? You can basically do anything you can imagine. You can write any script, you can add any binary, you can do whatever you can imagine. But because you have so much power, it's really kind of a weakness as well, because, with great power comes great responsibility, as you can imagine. So to build what we call good Dockerfiles that are compliant with best practices, this is actually quite hard to be consistent, to be secured, to be continuously patched and made sure that it is according to all the best practices. And this is really one of the main challenges with Dockerfiles. Now, if you go to Docker Hub and you see the Dockerfile best practices, you're going to see multiple recommendations. You need to create ephemeral containers. You need to understand how the build context works. You need to pipe the Dockerfile through std-in. How to use multi-stage builds, etc., etc. The list is quite long. This is just a very simple, a shortened list of the required parameters to create a correct Docker image. Here's just an example of the official Python image from Docker Hub. It contains around 112 lines of code, right? Sorry, I'll be more exact. It actually contains 112 lines of the run command. This is just one aspect of the final Dockerfile, right? So this is a lot of stuff that you really, if you really want to understand what goes on in your image, it's quite cumbersome and quite hard to figure out by yourself. So Dockerfiles are, again, an easy way to get started. It's an easy way to get to a working application image. There are endless examples across the web, and you have precise control over what goes on into the final image. But the caveat is that you have quite a technical debt on your hands. You have to really understand exactly how things work in order to be certain that you can deploy the target image to a production environment. It's pretty hard to keep without any vulnerabilities. You have to continuously chase down CVEs. And the standards for a Dockerfile are really just people in the organization that define a standard. And it's not a platform that does that for you. As a result, you're lacking auditability, consistency, and repeatability while building your images. So that's exactly the sort of thing that Cloud Native Buildpacks is trying to solve. Okay, Buildpacks from buildpacks.io. This is the website for this project. A brief history: it started way back in 2012 with Heroku. They created the first version of the Buildpack specification, which was used for their cloud environments. At some point, the Pivotal Corporation was formed, and we took a bit, I came from Pivotal, so I say we took a bit of a deviation from the specification that Heroku built. So we basically had two different versions. Heroku had their own version of the Buildpacks, and we had our own version of Buildpacks. And around 2018, we basically joined hands and contributed a final specification version 3 to the Cloud Native Computing Foundation, and we called it Cloud Native Buildpacks. So that's where we are today. So there's quite a history with this project. It's all the way back to 2012. There are millions of images in production using this technology, so it's not something that just was created like yesterday, right? So what exactly does Buildpacks give us? It basically gives us the ability to take some source code, right? Any source code of an application, move it through a chain of these binaries called Buildpacks that describe how to process the source code. And in the other side, you're going to get a final working application image, right? So it's basically a declarative way to translate your application source code into a production image. Unlike a Dockerfile where you basically define the how, in a Buildpack approach, you kind of define the what. You basically say, well, I want a Java application. I want to use a Node application. Here's the source code. Make it work for me in a way. Now, as you saw, there's quite a big community adoption for the project. We at VMware, which acquired Pivotal, obviously has a lot of stake in this. We contributed the Pack CLI, which we're going to see in a few seconds. We contributed the Paketo set of open source Buildpacks, which we'll see later. But there's a much broader ecosystem, obviously Heroku and Salesforce and GitLab. Google Cloud Platform uses Buildpacks for the Google Cloud Run. Microsoft Azure uses it in Azure Spring Apps, and Weaveworks and Tecton. Quite a few projects use it across the landscape. So what do we get when we take source code and run it through this process of a Buildpack creation? So you finally get a working image, right? As you might expect, it's the same. The final result is exactly a Docker image as you would expect from a regular Dockerfile in a way, right? It's a compliant OCI image. It has operating system, it has dependencies, and it has your source code application compiled. And this is basically an application image that is runnable. It is reproducible, so if you will run through the same Buildpacks at any environment in the public cloud on-prem, you'll get the same result in the end. Obviously, it's deployable. The final image can run anywhere, just like any other OCI image. And it is something that's quite unique, which is rebasable. This means that I can basically change the underlying operating system without having to rebuild the image itself. We'll see that later on. But the whole idea is basically that you can patch the operating system without doing a full rebuild, which is a very big benefit. Okay. In recent versions of the specification, we also provide what we call bill of materials. So basically you get a report, SBOM as we call it, that lists exactly the versions of the packages and the build tools that are currently in your image. So this is very good for source code scanners, for all type of security tools, analysis tools, things like that. And as mentioned, it's in production for quite a long time. So let's see it in action. Maybe it will be easier to understand. So I have an environment here. I'm running this one remotely because my machine is an M1 machine, and running Docker images on M1 is kind of weird. So I figured let's just do it. Let's do it remotely on x86 machine. Okay. So you can see my screen, I hope. So I have a simple application here. Let's start with this Python app right here, okay? Just a simple Python application. It has a server Python application. We can see the source code. It just returns some greeting, as you can see, okay? It has a requirements txt file, which adds a dependency on the Flask, sorry. And this is just a standard Python application. So I can basically compile it, pip3 install -r requirements. And this is going to compile it. And once it's compiled, I can run it locally. And I get a server running. And this is just a different location of the same environment. So if I'm going to curl the environment, I'm going to get the response, right? This is just, like a local testing before I do anything with containers. So how will I take this application and build an image out of it? Well, one way to do that is obviously to write a Dockerfile, right? So this is how we usually do it. So here's an example of a Dockerfile. I just Googled, honestly, some version of a Python-based image of 3.7 and found this one. I'm copying the source code to the /app folder in my target container. I'm changing the directory to /app, and I'm running the same compilation command as I did locally. I'm exposing the port, and I'm saying run server.python, right? That's pretty much all I'm doing here. So this is a very simple Dockerfile, but you can see how granular I have to be to make things work. So let's build this. Let's call it PyApp and build a local machine. So this is compiling in the Docker container, and my application is now compiled. Okay, so if I'm going to run Docker run, I'm going to expose 8080, and I'm going to run the PyApp image that I just created. So now I'm getting the same answer, but it's time from a container, right? A Docker container running on this machine. It's right here. I can show it. Here it is. Okay, and if I'm curling the same host, I'm going to get the same response. Okay, so it works exactly the same. I can try to stop this image, but again, because I'm not exactly fluent in writing Docker files, I probably didn't take care of sigterm correctly, so it doesn't work perfectly as I would like. So I can just stop the container directly here with a stop command. Okay, and now it's stopped. So this is how we do it with a Dockerfile, right? Very simple to get started, very easy to get going. But obviously there are problems. If I were to take this image and run it through a security scanner, I'm probably going to get an endless list of vulnerabilities at this point, because I think I wrote this sample application like, I don't know, 2 years ago, and I keep using it for demos, but I never really patched the base operating system. I never patched the Python runtime. I never did any of these things. So it's quite logical that the version that I'm using is already out of date and incredibly insecure, right? Now, how can I build the same image, but using cloud-native buildpacks? So in order to do that, I have a CLI called kpack. Okay, this is something we provide out of the box in the open source community. This is basically a CLI for building applications using cloud-native buildpacks. You have a lot of options here. We're going to use a fairly simple one. We're basically going to build. So I'm going to run, sorry, let me copy this. So I'm going to run pack build PyApp, and I'm going to give it again a path, local current directory, and I need to give it a builder. We'll see later what that means. What is a builder? So I'm not going to provide one. I want to see the options it gives me. So in this example, it gives me, well, you should probably use something like, I don't know, a sample builder, Bionic or something like that. So let me provide Paketo Buildpacks builder base. This is something that I know works. So let's see what happens here. This would work if I have a Dockerfile. If I don't have a Dockerfile in the folder, it doesn't use it at all. It ignores the Dockerfile completely. So it basically took the source code, it began analysis, right? And then it started detecting which build packs make sense for the context of my application. So in my application, I need certificates, I need compilation of Python, I need pip install, I need Python start, and I need a proc file. Based on the existing build packs in the open source community, these are the type of build packs that make sense for my source code. It actually went through the source code, and for each one of the available build packs he has in the open source community, it says, does this particular build pack make sense for this application? And each one returns true or false. So I have 6 of them. Then it does a process of restore, which makes more sense for subsequent builds because it improves caching and things like that. And then it starts building. With each one of these build packs basically runs a build command. So I'm compiling with CPython, I'm configuring environment variables, I'm reusing cached layers because I already built this once in this environment. And eventually it creates a start command, a proc file, Python server py. I didn't have to write anything to tell him how to do it. It basically figured it out based on the specification. Okay. Then it created all the layers and it successfully built the image. Okay. So now basically PyApp is an image built with Cloud Native Buildpacks. So if I'm going to run the same command as before, Docker run, again, I'm getting pretty much the same experience and I can curl it just like before. And now because, Buildpacks know how to build images, I can also stop the container with a SIG term, okay? So this was a very, very simple baseline example of how it works. Now let's see behind the scenes what really happened, okay? If there are any questions at this stage, happy to answer them and maybe we can move on to the underlying details now after that. All right. So let's see what happened here. We basically ran this command, pack build with the source code with a particular builder that came from the internet, right? And it gave me a working image. So what actually happened here? So we saw the phases, the life cycle of building an image with Cloud Native Buildpacks. There was detect, restore, analyze, build, export, and cache. Let's take a look at each one of them in detail. So the process of detect basically tests the source code that I provide as input against groups of build packs that are available to them, okay? The first one that passes is the one I'm going to use in order to actually build the final image. So let's see an example. So if I have a source code, and in my source code, I have both a package JSON and a yarn.log file, and I have 2 groups of build packs available in the environment. One of them combines Node with Yarn, and the other combines Node with NPM, right? This is a Node application, obviously. So for this given source code, which one will actually be used? As you might guess, the one that's going to be used is the first one because the detect for Node looks for package JSON, the detect for Yarn looks for a Yarn lock, right? So this is the group that's actually going to execute the final image creation for me. If I were, for example, only had the package JSON without a Yarn lock file, it's just going to choose the other one because this would not pass validation and it's going to move on to the next one on the list, okay? So this is how we choose which group of build packs to execute against my source code. Once I selected the group, I begin a process called restore. So a restore basically is used, as you see the last step here is caching. So let's imagine I already built the first version of this image, and now I build version number 2. I change my code and I want to build it again. So this is basically taking any layer that should have caches. Think of OpenJDK, Maven caches in Java, Python dependencies, NuGet packages in .NET Core, whatever it may be. It's going to basically cache it as a local or to the local disk, depends on where you run the build itself. And it's going to restore it and basically saves me a lot of time because I don't have to go out and download dependencies every single time because it's already saved somewhere, okay? Then I'm going to start a process of analyzing the source code itself, gathering some metadata, and understanding exactly what layers has to be built to the final image. And then for each one of the build packs in the group is going to run the build command. Each build pack has a different implementation of the build command, as you might imagine. So a Node build pack will run Node compilation. A Spring application might run Maven Spring boot build image. A .NET application might do .NET restore. Each one of the different languages in the world has its own use case of how it should be built correctly, right? So for each one of these build packs is going to call a binary called build in order. Each one of them is going to generate its own layer for the final image, okay? So it will gather dependencies, compile the application if needed, and then eventually define a launch command. Basically, what we needed to do manually in a Dockerfile, this is done for us automatically. Then we have the export process, which basically assembles all these layers that were created into a final compliant OCI image. And depending on where we run it, it might even push it to a Docker registry in the end, okay? And eventually we cache the results so that the next time we run the build, the restore process doesn't have to do all the work again. It can use caches as needed, okay? So this is pretty much the flow that we just saw. There is a new addition to the specification, which is being implemented right now, which is called extend. This is basically based on feedback because many times there were requests, I want to do something extremely unique and custom and unpredicted that the default build pack for a Java application or for a Python application cannot do. Maybe I want to go out, make an API call somewhere. Maybe I want to execute some batch job, whatever it may be. So the extend is basically a part of the lifecycle where you can actually give it a Dockerfile now, so it can do anything you can imagine during the process. Okay, so this is a very powerful addition. So you can make build packs both compliant and repeatable, but also extensible if needed. So let's try to understand this builder. As you remember, when I ran this command, I basically told it, build the Python application with the local source code and use this builder, Paketo Buildpacks builder base, right? What is this builder? What does it do? Where does it come from? So a builder, well, let's talk about the stack first. A stack is a set of two images coming from some registry, right? There's a build image and there's a run image. The build image is where we're basically going to build our final OCI image in. So we actually run the build process inside its own container. Why do we want to do that? We want to make sure that the process of building the image is repeatable, consistent, and validated, right? So we have to know that the build environment is always the same. That's why we even build the actual container in a container by itself, okay? So there is a build image for the build time environments, and there's a run image, which is basically the base operating system, which we're going to use to actually run the final artifact image, okay? So the build image is going to do the whole process. Basically, everything we saw happened in a container on that machine. It ran through the lifecycle, it built various layers, etc. So the builder is the complete context required to build an image. It's basically the build image itself, as you imagine, like this base image here, which probably like an Ubuntu machine or something like that. It contains all the build packs required. So you have like, I don't know, in a common builder, you might have 20, 30 builders, right? And each build pack, and each one of them is going to build whatever layer it needs. So it contains all of these binaries in the same image, so we can easily make reproducible builds out of it. And as you can imagine, it contains the build pack binaries themselves. So as you can imagine, these builders are quite unique. Everyone can make their own builders. You can make your own. The most popular ones are those built by VMware. This is what we just saw. We basically use the Paketo Buildpacks here. This is a publicly available open source implementation. There's also one from Heroku, which is a very popular provider for build packs, and Google makes their own versions as well. Okay, So if you take a look at the big picture of what happened here, we basically took the source code to this platform, which in our case was just a simple local binary. We fed it the source code, we fed it the builder image itself, and we basically ran through the process in order to create a final runnable image, right? This is the one we just ran, the SPI application that contains the base operating system, the dependencies, and the application itself. Now, one of the main features of an image created by Cloud Native Buildpacks, as I mentioned before, is called rebasing. So rebasing is our ability to change on the fly the underlying operating system without having to do a full rebuild. When you need to change a base operating system in a Dockerfile, you have to run the entire flow, Docker build with the updated Dockerfile, and it's going to run through the entire installation, which could take minutes, if not more, depending on the size of your application. In the context of Buildpacks, you basically can do it without any rebuild. How do we do it? We basically use a remote registry manipulation, very similar to how Git does the rebasing of branches and things like that. We basically change a pointer for the underlying layer to a different base image, right? So we can just make an immediate change in an image without a full rebuild. And we have the ABI guarantee, which is an application binary interface guarantee, to make sure that our application behavior is preserved so we don't break the actual application because we changed the operating system. All right, so that was a very quick explanation of the underlying features of Buildpacks. If there are any questions, I'm happy to answer them now. And here. Okay, so if there's no questions, I will move on. So let's discuss about the reason behind this project and why we really created it back in 2012 and how it continues all these years. So one aspect is really empowering operators. It's basically making sure that when you have images built in your organization, in your enterprise, in your startup, or whatever it may be, you can basically have the guarantee that the images themselves are going to be as expected. So, if you just look at the top 10 popular Docker images with the vulnerabilities on the internet, you're going to see that there's just endless vulnerabilities in the ecosystem. And the interesting part about this report, this one is from Snyk, is that if you would just rebuild the image without changing even the Dockerfile, in 20% of the cases, the vulnerability would basically be fixed automatically because you might pull the latest version from the internet. And if you're able to just replace the base image, basically like we did with the rebasing technology, that would result in 44% of the images being patched automatically without having to do anything. So as you can imagine, there's a lot of benefit when you can have this type of technology that does these things for you. So for operators, it's a very easy way to patch CVEs. It proactively manages approved technologies. You can define which build packs you want in your organization, and this will be the only vetted technologies inside. You basically have, the ability to define exactly what you want to have, and each developer and operator does its part, and both can work together very, very easily. For developers, as you might have seen in the demo, it's kind of magical. I didn't really have to do much. I didn't have to think about how this really works to get it working. I just said, here's my source code, build an image for me. I don't care how, right? And this is a very powerful feature for developers. They don't have to think about the how. They don't have to write Docker files, which can permutate endlessly. And you can basically make sure that anywhere you build your target image, if you currently develop on your laptop and you run pack build, and then you move to a production environment, some Jenkins job and run pack build, both of them are going to produce the exact same final image if you were to use the same builder behind the scenes, right? So this is a very powerful guarantee that nothing will change along the way. Again, because of the caching built in, only rebuilt images will be changed. So it's automatically caching itself. and you can really focus on value and don't have to think about the underlying technologies. Now, we saw that there are multiple builder implementations, and in our example, we used the Paketo Buildpacks implementation, which is contributed by VMware to the open source community. It is really a set of build packs that are designed to basically give a working set of defaults if you don't want to use anything else, right? If you don't want to go out and buy like an enterprise supported version of build packs or things that need to work in air-gapped environments or whatever it may be, you can basically use the Paketo build packs. These are like the de facto standard build packs in the world today. Now, the reason we really need them is, as you might have seen, I had to provide a builder because the specification does not provide any implementation at all. It's just the spec itself for how to basically create these final images. So the Paketo build pack basically gives me the ability to have a same set of defaults that I can reuse every time I want. And as you can see, there are multiple implementations available. Heroku has a SaaS platform to build images. The Paketo one can run anywhere, obviously also on-prem. Google implements their build packs as part of the Google Cloud Run. Microsoft has their own set of build packs, et cetera, right? So just an example of some of the build packs available out of the box in the Paketo implementation. It's all on GitHub. You can see everything, how it goes. All the development is done in the open. You can create pull requests. You can open issues. You can ask the community for support, which is very, very nice. So we basically saw how I can build an image on my own machine. And, you know, that's very, very nice because sometimes I want to develop locally and I want to make sure everything works as expected before I move on to the other tasks. Before I continue, I see there is a question here in the chat. Can we point the build packs to build and push an image to cloud-based registries and point the runners to point to a different containerized runtime? Okay, so when you run the build, basically a container starts wherever you have the implementation running. In my case, it ran on some VM. So it basically created a VM in the Docker container, in the Docker engine running on that VM. That's where the build image was created and build the image. And the final image can be pushed wherever you'd like. It can be pushed to ECR, to Google Cloud Registry, whatever you might have available, right? Now with kpack, I'm going to show you how it can basically be completely built remotely and not on my machine where I'm running the commands themselves, okay? Hopefully that answered your question. So kpack is really when I'm starting to scale, right? So I built my own image. That's great. That's very, very useful. But at some point, I'm going to maybe have 20 images, 500 images, 1,000 images. This doesn't scale for a local machine. This is getting impossible to handle. So that's really the purpose of kpack. So again, Pack is the great tool to get started. There are implementations if you're a Java developer and you're using Spring. So Spring has just a built-in plugin for build packs. You can basically run Maven Spring Boot build image. It's going to build the image for you with zero Docker files right from Maven. So there are multiple implementations for that. So Pack is the de facto standard for building locally, but it is mostly for local development. It's not exactly optimized to do like high volume builds and at scale and across nodes and things like that. So let's see what happens and why we really need some sort of a main build environment in an organization that manages this at scale, right? So because we mentioned before that building secure images is rather hard, you have to basically chase your own tail all the time. You have to find vulnerabilities. But really, the biggest challenge is to keep them secure, right? So you build them once, everything works great. You pushed it to production. 6 months later, you might have like 20 CVEs already, because if you don't touch it, then it's just the CVEs are being added every single day. Let's see how it works in a case study from 2016 with the Heartbleed that you might have heard of, one of the most critical SSL vulnerabilities ever. And let's take this typical Node.js application. When I'm writing my Dockerfile in day one, everything works just fine. I choose some base operating system, let's say Alpine. Alpine behind the scenes requires an OpenSSL, so it installs OpenSSL. And from there, I'm using my base image. And, I do the regular dance. I copy files, I run npm install, I do ng-serve, whatever it may be, so my application will work as expected. And I can take this image through a scanner and I'll get 0 vulnerabilities and everything is great, right? And then I deploy to production. And after several months, something like Heartbleed comes out. And basically, I now have a very critical vulnerability in a running image in production, okay? Which I wasn't even aware of when I built the image itself. Now, this is, again, a problem when you have like 1 or 2 images, but when you have like 200, this is really, well, the challenge begins. I'm basically have to go over each one of these and now figure out where the problem is. It can be quite a nightmare. And this is, the sort of nightmares that organizations faced with Heartbleed, with the Log4j vulnerability. This is something that's not new. It's like it kind of a repeatable pattern every time we see it, that suddenly, our customers that use Buildpacks are like, wow, we basically are secured from day one. So if we do Dockerfiles, what you call wrong, where we basically let every team choose its own base image, some organizations want to do it. They want to give freedom to their developers. If you had this vulnerability in that use case, each one of the teams might have chosen a different base operating system. One might go with Ubuntu, another one with Alpine, the other one with CentOS. Maybe someone would just go from scratch and build its own container image. Now, each one of them, you have to go one by one, figure out if it has a vulnerability, and if it does, what version of an operating system fixes that, right? So this is like an endless process when you have a lot of images. Now, if you were to do it with a more strict compliance, where you basically say, well, in our organization, everyone is using Ubuntu, version trusty, or whatever it may be, right? So in this case, you'd still have a problem because now you have to basically rebuild and retest the images because you rebuild the entire image, and obviously eventually redeploy this application. And the main challenge is that it is operator managed. You basically handle it yourself. This is a non-functional requirement that you have to have ready to go in your organization. So kpack tries to take a Kubernetes way to build container images at scale. And it uses Buildpacks and Paketo behind the scenes. But the whole point of kpack is really to be this Kubernetes-based runtime to build images for multiple teams in an organization, right? The way it does it, it basically extends Kubernetes with custom resource definitions. And behind the scenes, when a command is issued, it launches a pod. So now the container does not run on my machine. It runs in a remote Kubernetes cluster. That pod is going to load the build image to compile my application with Buildpacks. And then it's going to push the run image that is created to a remote registry, right? So everything is basically now done remotely in a scalable fashion. Each team might get its own namespace. You can have multiple worker nodes, each working together, and you can build hundreds of images at scale. So we mentioned rebasing. Again, that's the same point. So let's see how it looks for real. So for example, I have these like 100, 200 images with a vulnerability of OpenSSL. And this day comes where suddenly I have the vulnerability. Well, if you were using something like kpack and you get a new updated build pack that solves the problem, you just issue a single command and 200 images are now pointing to the correct base image automatically, right? So the result is that you can deploy or basically rebase 500 images in seconds, and maybe you just need to redeploy these images, which could take a bit longer. But you don't have to rebuild or retest the functional application because you have what we call application boundary interface, which is a guarantee that the operating system will not break your application code. So this is a very, very powerful feature. So let's see how kpack works. So I'm going to close this and I'm going to close that. And I'm going to use my local machine now because I don't build anything on my machine with kpack. I do everything remotely. Okay.
We got
so
a question, by the way.
Sure. Let's see.
In the chat.
Does it produce a new image hash or it patches the existing one? Yeah, it does produce a new image hash, absolutely, because we basically never use like a latest tag. We always use a SHA-256 signature, and the new image is going to have its own tag in the Docker registry. Okay. Okay. I hope this is big enough. So I have a Kubernetes cluster here. This is running, in my case, on vSphere, but it can be GKE, it can be EKS. I really don't care where the Kubernetes cluster is running. Okay, and I have kpack installed here. I actually have the enterprise version of kpack called Tanzu build service installed, but it's exactly the same, just with additional features for air gap, for support and things like that. So kpack has its own CLI called KP, which just lets me see things use things more easily. So I can run something like a KP image list. Okay, and this is going to return for me all of the images that are currently running in my environment. Let me resize this a bit. Okay, so I'm currently at a cluster called tap iterate at a namespace called demos. And in this namespace, I have multiple builds happening at every single time, as you can see here, right? So I can also use kubectl because this is just Kubernetes at this stage. And I can say get kpack images kpack.io, right? And it's going to return basically the same information just with kubectl. Okay. And each one of them is its own image managed separately. So let's just create a new image. And again, this time I'm not going to build it locally. I'm going to build it remotely on the Kubernetes cluster. So I'm going to do kp image create. I'm going to build an application called Spring on Kubernetes. I'm going to give it a tag. This tag is basically where I'm going to push the image to at the end of the process. So this is my Harbor instance. It can be ECR or anything you might have today. And I'm just going to point it to a Git repository this time. I'm not even going to point it to a local repository. So I have this very sophisticated Hello World application here. Again, basically returns a hello world from Spring in this case. And the application in this context looks like this. So it basically returns a hello world with Spring. Okay. So I'm going to give it the Git repository and the revision, the branch, which is main. I'm going to hit create. Okay, and it says, okay, image is being created. Nothing happens on my machine at this stage. I can now run kp build list for this Spring on K8s. Show me what is going on behind the scenes. So it is telling me, well, one build is currently running, okay, because you just created the first configuration. If I'd like, I can also request the logs so I can see what it's doing on the pod itself. So here's the same flow as before that we saw. We're basically, this time we're taking source code from Git. We're not using a local location. We're analyzing the source code. We're detecting the build packs to use. This time I'm using 11 build packs from a total of 43. So in this case, unlike the Python example, this time I have OpenJDK, which is this Bellsoft Liberica. I have Maven, I have Tomcat, I have distributed zip, I have Spring Boot, right? So based on the source code, the build packs change, as you might expect. For the first time, there is no caches available because this is the first build, right? And then for each one of the build packs, it runs the build command. So this installs OpenJDK, right? And this compiles with Maven. So this is basically what it did here. It compiled, it finished successfully. Here it defines the executable jar. Here it configures the Spring Boot to start correctly with all of the various environment variables. And eventually it's doing the export. So what we have here is reuse of cache layers, and then we basically save the target image to the remote registry. So this is the SHA-256 for this image. It's pushed to the remote Docker registry, and it also got a tag build1 with the current timestamp. Okay. So if I want, I can take this and say Docker run. And basically run this image. Okay. I don't have Docker running. This is funny. Yeah, I restarted just before the session began. So let's give it a second to boot. And it's basically going to run this locally for me. While this is happening, let's make a code change. So I'm going to go here, and I'm going to say, instead of hello world, let's say, how do you say hello in Bulgaria?
I typed it in the chat.
I hope this will work. Let's see. All right. Oh, someone wrote in English. Okay. Let's see if UTF-8 works correctly on my machine. So I basically changed the greeting, right? All right. So Docker seems to be running. So I'm going to run it now. Again, the image is not available locally. So it's going to pull it for me from the remote registry. And then it's going to start up. So here's the Spring logo. And it's going to be a bit slow because, again, I'm doing a translation from x86 to M1 in my case because it was built for x86. But it's going to boot in around a second or two. Okay. And here it is. It's running. And if I go to localhost, I get the hello world. While I did all of that, we did a git commit. So I believe that if we, again, show the list of builds for Spring on Kubernetes, it is going to say, no, it didn't. Maybe it will take a few more seconds. It should basically say that I got a new version of the image committed here. And once that happens, it's going to trigger a new build. Now the demo god should be with me. Let's see. Demos never work. You know how it is. So basically the idea is that let's take a look at some of the other images I have here. So for example, if I take this, I don't know, this Tanzu to-do service, okay? KP build list for to-do service. So as you can see here, I have two builds because I made a code change in the Git repository, and that triggered a second build. And once it triggered, it's going to basically build it again. Give it one last chance. Yeah, probably has a long interval to check for changes. So the idea here is basically that you can see I have multiple builds happening in multiple namespaces. Each one of them is running in its own build pod. We can see them here. Let's, for example, grep Spring on K8s. So you see I basically have a Spring on K8s build, one build pod. So everything ran as a job in Kubernetes. It took about 5 minutes the first time. And this is the process that built the final image for me and pushed the image to the remote registry. Okay, so this is how you're basically going to have multiple images running at parallel at the same time. So to summarize, Buildpacks is a way to do repeatable builds, is a specification to do repeatable builds. It's being used across the CNCF, across the industry. Pivotal back in the day, and Heroku contributed it, and now VMware is really leading the pack with this. If you go to buildpacks.io, you're going to see multiple tutorials and the specification itself and documentation. Paketo.io is a very good place to go to get some example of the open source Paketo Buildpacks. You have documentation for each one. For example, if I want to understand how do I properly build a Java application, so obviously you can just use the defaults, but as you can imagine, every single one of these build packs has a lot of customizations that you might want to implement. For example, I want to change the build tool. I want to change the Java version. I want to, I don't know, specify a larger volume or whatever it may be. Maybe increase the number of loaded classes or a thread count or anything you can imagine. Maybe even change the JVM itself, the OpenJDK I'm going to use as default. So all of these are documented very clearly here, and you can basically play with it and almost make any changes you can imagine here, okay? So Paketo is really the way to go. Tanzu Build Service, just as a reference, is the open source implementation of what we just saw, the kpack solution. So this is really how you can take the Kubernetes solution of kpack and run it at an air-gapped environment with the enterprise-supported Java build pack, you know, all of these good things that you can imagine. And, you know, there are tons of examples on GitHub in buildpack/samples, and you can really take a very deep dive. You understand exactly how these things work behind the scenes. That's pretty much all I had for you today. If there are any questions, I'm happy to answer them now. I'm giving it one last chance, and no, it didn't work. Too bad. Yeah, let's see. I'll stop the share. Is it possible to onboard migrate existing images to kpack managers, or we need to use the source code to rebase rebuild? Yes, so you basically take the same source code. I would say it, I think like 89% of the use cases, just if it's, a standard modern language, Node, PHP, Python, .NET, Go, Java, things like that, it will just work without you having to basically change anything. You might have to give it some environment variables if you want to force a specific version of a JDK, of a .NET runtime, things like that. Beyond that, there's really not much to it. It should just work out of the box. Okay. Any other questions? You can unmute, you can write, whatever you prefer. All right. Hope this was informational for you. Thank you very much for the time.
Thank you, everyone. And please note, when you leave the meeting, you will receive a questionnaire. Your feedback is quite important to us, so we can keep improving this series, the topics that we present, because we're doing this all for you. So your opinion matters, and we want to hear from you. Again, it's anonymous, so be honest. And thank you very much for your time. Thank you, Oded, for the presentation. Quite interesting. And look forward to seeing you, everyone, next time.
Have a good day. Bye.
Have a good day, guys.